Hello everyone. Today we are going to learn about basic VHDL program for shift register. That is a serial in, serial out shift register. Before learning that, let us see what is a register. The register is a temporary storage location present inside a CPU. The basic building blocks of a register is flip-flop. You can use any type of flip-flop. Here we are going to implement with D flip-flop. To design n-bit register, we need n number of flip-flops. And then we can design a shift register. What is a shift register? The register whose contents gets shifted for every clock pulse is called a shift register. And this data can be shifted in the register either serially or parallelly. Based on that, there are different types of shift registers. One is serial in, serial out shift register. That means data enters into the register in serial manner and comes out of the register in serial manner. Similarly, serial in, parallel out, parallel in, serial out, parallel in, parallel out. Like that, there are 4 different types of shift registers. Now we are going to consider the serial in, serial out shift register. So in, serial out shift register, the data enters into the register serially bit by bit for every clock pulse. And at the same time, data comes out of this register serially for every clock pulse. The data to be shifted can be entered into the register either from MSB or from LSB. If the data enters at MSB comes out from LSB. If the data enters from LSB comes out at MSB. Now in this case we are seeing the data entering in MSB side and therefore it comes out at LSB side. So shifting is taking place in right direction. Therefore we call it as serial right shift. Serial in, serial out, and it is right shift. Now, same thing can be implemented with the flip-flops, and we are going to implement with the D flip-flop. So we are writing VHDL code for 8-bit serial in, serial out shift register. Therefore, we have considered 8 D flip-flops. Each flip-flop stores 1 bit of data, right? And D0, D1, D2, D3, D4, D5, D6, D7. And D flip-flop has another input, that is its input DA, DB, DC, DD, DE, DF, DG, DH. And all the D flip-flops have their respective outputs QA, QB, QC, QD, QE, QF, QG, QH. That is nothing but S out. And here it is serial in. And for D flip-flop, we have to apply clock pulses. Therefore, clock is applied to all the flip-flops. Clock, 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 clock. Right? Clock is applied to all the flip-flops. Now, we also apply clear signal to clear the contents of the register. Therefore, we use clear bar here, and it is an active low signal. Therefore, clear, 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 clear. Right? So like that, we can understand what are the various inputs and output of a flip-flop if we consider one element here. QA is the input, clock and clear signals are also the inputs, and sorry, DA is the input, clear bar and clock signals are the inputs. So 3 inputs are there, and QA is the output. So if you consider one element and if you declare one element as component, we can have port map and we can write the structural style of modeling and architecture body for this serial in, serial out shift register. So same thing can be expressed here in truth table form. So clock signal, clear bar, serial in, and all 8 D flip-flops outputs QA, QB, QC, QD, QE, QF, QG, QH, and out, serial out, therefore S out. Okay, and input data we are applying at MSB, therefore we have written here, and LSB side we are taking output, therefore we have written S out here. Now, if there is no clock pulse applied, irrespective of clear and input signals, the contents of the register will be same. That means as it was in the previous case, therefore we call this condition as hold state. Okay, then when we apply clock pulse and when you give clear bar 0, that means clear signal is active low signal. Therefore, when we apply 0, irrespective of the input, the contents of the resistor will be 0. That means it is cleared. So like that we clear the contents of the resistor. Now when you apply clock pulse and when you disable this clear signal, and then when you apply input serial in at the input port, when we apply 0, that 0 will be entering into first flip-flop, that is QA, that means D0 flip-flop. QA will be 0, and whatever is this 0 will be coming here, and already whatever is there in QA, that will be shifted to QB. So here QA comes here and QB here and QC, QD, QE, QF, QG, and whatever is the contents of H uh, last day flip-flop, that QH will be coming out as S out. Okay, so QH will be written here. So QH is S out. And similarly, when you apply clock pulse and when you disable clear signal, and at the input if you give S in, serial in, then that will be applied to for each clock pulse. That is S in will be shifted to QA and the QA contents will be shifted to QB, and similarly here QB, QC will be shifted here, QD, QE, QF, QG, and whatever is the contents of QH will be coming out. Like that the output is shifted. That means QH is nothing but S out when Sn is equal to 0. So the 8-bit shift register which is implemented with D flip-flop can be represented by using this truth table. Now you might have followed this theoretical concepts. Now after understanding this, let us try to write a VHDL code. If you understand these concepts, please share this same video to your friends also. Like, share and subscribe our channel for future videos. Now let us see the library and entity declaration for this. So library IEEE, use IEEE.stdlogic1164.all. We are using only this package, stdlogic1164 package. If you are using other aspects, you can also incorporate other packages. Now entity, name of the entity is, so what is the name of the entity? SISO register is ports. Let us mention what are the various ports in this D flip-flop, right? I mean in this register. So S in, and let me show you this. S in, clear, clock, clear. These are the inputs, and S out is the output. Okay, so therefore let us write this entity like this. Input ports are S in, clock, clear. These are the input ports, standard logic type, and S out is the output port with the standard logic type, and name of the entity, that is SISO register, right? And we are going to write structural style of modeling. So therefore we go for component declaration. And before we go for component declaration, we have to ensure that the components used in the architecture may be the ones that were previously defined as part of a design, or they may be part of a design library. That you have to keep in mind. Now let us see the architecture body. Architecture, a structural style of modeling of this SISO register. So I have given the name of the architecture like this. Of entity name SISO register is, and we have intermediate signals. Just I have shown you signal S1, S2, S3, S4, S5, S6, S7. All these are standard logic type signals. D0 to D1 signal S1 is there, D1 to D2, S2 is there, right? I think for your convenience sake, once again, I will show this is S1, S2, S3, S4, like that up to S7. So these are the signal declarations we have to make here. Then component D flip-flop, and for D flip-flop, we are giving three inputs, that is clock signal, clear signal, and serial data input. So I have given the names of the ports as data 1, clock 1, and clear 1. These are the input ports to D flip-flop. It is standard logic type. And output port, I'm mentioning it as output 1, output port, which is also a standard logic type, end component. So this is D flip-flop component declaration. Now begin the architecture body we are writing. So D0 is the D flip-flop port map with S in, clock, clear, and S1. Let us see this. D0 is port map with S in, clock, clear, and S1. Similarly, D1 port map, D1 is nothing but D flip-flop port map with S1, clock, clear, and S2. And similarly, D2 is D flip-flop port mapped with S2, clock, clear, and S3, right? So like this, we can write all the statements. D3 is D flip-flop, otherwise D0 is D flip-flop port map with S in, clock, clear, and S1. And S1 is input to next flip-flop. S2 is the output of the same flip-flop. So D1 is D flip-flop port map with S1, clock, clear, S2. Similarly, we can write all the uh, statements up to D7. What is D7? D7 is D flip-flop port map with S7 is the input to this, and also clock and clear signals. S out is the output of this D flip-flop. And after that, end structural style. That means end the architecture name. So in this way, we can write the VHDL program for serial in, serial out shift register. Hope you have followed this lecture. And let me show you the entire program like this: library declaration, entity declaration, and architecture body in structural style of modeling. So if you understand, you please like, share, and subscribe. Thank you for listening.